January 24th, 2025, 2:19 a.m. The first tremor struck Santorini, launching over 28,000 earthquakes in just 6 weeks. What scientists found beneath the island was more terrifying than anyone imagined. Moving fault lines guiding magma between Santorini and the hidden Colombo volcano. If this volcanic highway erupts, entire coastlines are at risk, but are the warning signs being missed? The next seconds could shape Europe's future. In the pre-dawn stillness, the island's seismic dashboard flickered to life. Automated sensors scattered across Santorini's caldera and clustered on the slopes above Fira registered a sudden spike, an unmistakable anomaly, sharp and out of sequence with the usual background noise. Within minutes, the alert protocol snapped into action. Algorithms flagged the event as a possible volcanic tremor, not just another minor tectonic jolt. At the GFZ Helmholtz Center for Geosciences in Potsdam, the monitoring team watched the live feed from the Aegean. The waveform's jagged signature left little doubt. Something deep beneath the island had shifted. The island's civil defense system received the first digital ping, followed by a cascade of notifications to regional authorities. In the main monitoring room, Dr. Marius Iskin, a volcanologist known for his calm under pressure, checked the preliminary data. The event's depth and character set it apart from the routine tremors that sometimes rattle the caldera. This was not a shallow aftershock or a distant slip along the Hellenic Trench. The signal hinted at movement from within the crust, a possible intrusion, the kind of activity that can precede volcanic unrest. By dawn, the incident log showed a cluster of similar signals, each one tripping the network's sensitivity thresholds. The system's automated scripts began compiling a timeline, archiving every blip and spike for later analysis. The early hours saw a flurry of encrypted messages between Greek Civil Protection, the National Observatory of Athens, and international partners. Standard protocol called for round-the-clock vigilance, continuous waveform analysis, cross-referencing GPS data for signs of ground deformation, and real-time communication with local authorities. No one could say yet whether this was a false alarm or the first sign of a deeper crisis, but the urgency was unmistakable. On Santorini itself, most residents slept through the initial tremor. The island's narrow streets remained quiet, the only movement coming from the blinking lights of seismic instruments and the silent exchange of data across the continent. For the scientists watching from afar, the night's events marked the start of a new chapter, one that would test the limits of their technology and the resilience of the island's people. The initial tremors were only the beginning. As the hours passed, seismic stations across Santorini and the surrounding Aegean started to capture a pattern that was impossible to ignore. Earthquakes multiplied, their epicenters plotted by automated algorithms and cross-checked by teams in Athens and Potsdam. Each event was assigned not just a location, but a depth, a crucial clue to what was unfolding beneath the island. In the first days of the swarm, most earthquakes originated deep below the surface, between 8 and 13 kilometers down. This is the lower crust, a place where magma pools and pressure quietly builds. But the sequence did not remain static. With each passing day, the cluster of seismicity crept upward, tracing a vertical path through the crust. The migration was not a straight line. Some quakes appeared to leap laterally, shifting northeast toward the submarine slopes between Santorini and Colombo. The swarm's deepest events gave way to shallower bursts, with many epicenters converging at depths of 4 to 6 kilometers, just beneath the caldera floor and the seabed beyond. Seismologists mapped this journey in real time. Hypocenter charts filled with color-coded dots, each representing a quake at a specific depth and time. The upward march, punctuated by occasional pauses and lateral jumps, mirrored the classic signature of magma forcing its way through solid rock. Over 28,000 earthquakes were cataloged in less than 2 months, a number that dwarfed previous unrest episodes. The swarm's northeast drift, away from the traditional center of the caldera, pointed directly toward the Colombo submarine volcano, suggesting a magmatic connection that scientists had only theorized until now. Instrument networks, both on land and on the seafloor, provided an unprecedented view of this migration. AI-driven analysis allowed for rapid relocation of quake origins, reducing uncertainties to within a kilometer or two. The data revealed not just a vertical ascent, but a branching, vein-like pattern, evidence of magma exploiting ancient faults and fractures. This was not the random rattle of tectonic plates. It was a systematic, pressure-driven intrusion, carving a new path beneath the Aegean. Each event, each shift in depth, told the story of molten rock on the move, pushing ever closer to the surface. The pattern was unmistakable. The island's unrest was being driven from below, and the crust was yielding step by step to forces that had shaped Santorini for millennia. Sensors planted across Santorini's volcanic rim began to tell a new story. GPS receivers, anchored into the bedrock above Fira and along the Camini islets, started to drift upward, first by millimeters, then by several centimeters. InSAR satellite images, processed in labs from Athens to Potsdam, revealed a swelling pattern that was impossible to ignore. The caldera, silent to the human eye, was rising as if the island itself had taken a deep breath. At the heart of this movement, a colossal volume of magma, estimated at 300 million cubic meters, forcing its way into the shallow crust. That's enough molten rock to fill more than 120,000 Olympic swimming pools, packed beneath the villages and vineyards that ring the caldera. The numbers, checked and rechecked by analysts, left no room for doubt. This was not a minor fluctuation or a routine cycle of inflation and deflation. The uplift was widespread, extending across the main island and the submerged flanks to the northeast. For the scientists monitoring the data streams, every spike in the GPS time series meant a new calculation, a new model to test. Teams worked around the clock, comparing ground-based stations with satellite passes, hunting for errors or signs of instrument drift. But the signals held steady. The crust was deforming in real time, stretched by the weight and pressure of ascending magma. Operators at the National Observatory of Athens and the GFZ Helmholtz Center knew what these numbers meant. Uplift on this scale, several centimeters across an entire volcanic island, signaled a massive transfer of material from deep reservoirs into the upper layers of the crust. The ground itself was responding to forces miles below, and the entire monitoring network was now on high alert. Each new reading offered a glimpse into the invisible machinery beneath Santorini, as the island's surface quietly recorded the restless movement below. Far beneath the Aegean, two continents wage a slow-motion struggle. The African plate, moving northward, dives beneath the lighter Aegean microplate in a process called subduction. At this boundary, slabs of oceanic crust are dragged deep into the mantle, carrying water, sediments, and ancient seafloor minerals with them. As the plate sinks, pressure and heat force the trapped water out of the rocks. This water lowers the melting point of the overlying mantle, creating pockets of magma that are anything but ordinary. These magmas are supercharged with water vapor and carbon dioxide, volatile gases that dissolve under immense pressure but want to escape as the melt rises. The deeper the magma forms, the more gases it can hold. As it ascends, the pressure drops and those gases start to bubble out, much like the fizz in a shaken bottle of soda. This is what gives Santorini's eruptions their explosive power. Unlike the slow, oozing lava flows of shield volcanoes, the magmas here are primed to burst. The Hellenic volcanic arc, stretching from Methana to Kos, is built on this relentless engine. Santorini sits at a bend in the arc, where the geometry of subduction and the weakness of the crust combine to focus magma generation. The island's very existence is proof of this process at work, each eruption a direct result of the ongoing collision deep below. Every pulse of magma, every earthquake, every uplift in the caldera can be traced back to the conveyor belt of subduction grinding onward, loading the crust with volatile rich melt. This underground alchemy doesn't just create magma, It sets the stage for the complex plumbing system that feeds both Santorini and the neighboring Colombo volcano. The chemistry and behavior of this magma, its readiness to explode or stall, are decided long before it nears the surface, shaped by the journey it takes through the collision zone beneath the Aegean Sea. Beneath Santorini and the nearby Colombo volcano, scientists have mapped a system of magma storage more complex than anything previously imagined in the Aegean. In 2019, Dr. Paraskevy Nomu's research team used seismic tomography and ground deformation data to reveal a branching network of magma reservoirs stretching from just 3 kilometers below the surface down to depths of 13 kilometers. These reservoirs are not isolated pockets. Instead, they act as interconnected chambers, forming what geologists now call a hydraulic network, a system where pressure changes and magma movement in one part of the network can trigger responses in another, even kilometers away. During the 2025 crisis, both Santorini and Colombo showed signs of simultaneous inflation and deflation, suggesting that magma was not only moving upward, but also laterally, traveling along this underground highway. Modeling of the crisis indicated that a single deep reservoir feeds both volcanoes with up to 300 million cubic meters of magma able to shift between storage zones. This cross-feeding potential means that unrest beneath one volcano can rapidly affect its neighbor, challenging the old idea that each volcano acts alone. The evidence now points to a shared dynamic system, one where the boundaries between Santorini and Colombo are drawn not by geography but by the flow of molten rock deep underground. Southwest to northeast, a web of faults cuts straight through Santorini's volcanic heart. These fractures aren't just scars from ancient quakes, they are active, shaping the island's future every day. In 2025, the earthquake swarm didn't spread at random. Seismic maps trace the events along these very fault lines, matching their orientation almost perfectly. Geologists have long recognized this alignment. The Kameni-Colombo fault system, running beneath both land and sea, acts as a natural conduit for rising magma. When pressure builds deep below, these faults become the preferred escape routes, guiding molten rock through the crust's weakest points. Sometimes, instead of pushing upward, magma exploits these lateral corridors, moving sideways for kilometers before finding a new place to rise. The 2025 swarm demonstrated this vividly, with quake epicenters migrating northeast from Santorini toward Colombo, following the mapped faults like a trail. This structural control means that eruptions don't always break out at the island's center. Instead, the real danger can shift along these hidden corridors, making the next eruption harder to predict. Every movement along these faults is a signal, a reminder that the island's peace depends on fractures that never truly rest. Far below the whitewashed villages and vineyards, the Aegean seabed hides a fracture that never truly heals. Bathymetric surveys carried out by oceanographers from GMR and the Hellenic Center for Marine Research have mapped a jagged corridor stretching from the base of Santorini northeast toward Colombo. This is not a single fault, but a chain of overlapping fractures, some wide enough to swallow a submarine, others no more than hairline cracks. Seismic reflection profiles reveal that these breaks slice through ancient volcanic layers, creating a continuous pathway for fluids, gases, and, at times, molten rock. The 2025 crisis exposed just how active this corridor remains. Earthquake epicenters plotted along the seafloor show a pattern that mirrors the faults mapped by sonar, confirming that the crust beneath the waves is anything but stable. Where the corridor dips deepest, sediment cores pulled from the abyss reveal evidence of past underwater landslides, triggered, scientists believe, by sudden injections of magma or the violent slip of buried faults. This hidden network does more than link two volcanoes. It acts as a fuse, carrying pressure and heat beneath the Aegean. In the wrong conditions, a rupture here could send a wall of water racing toward the coast, turning a volcanic crisis into a regional disaster. For the team scanning the ocean floor, the danger is clear. What happens offshore does not stay offshore, and the next warning may come not from the land, but from the deep. Long lines snaked down the cliffs before dawn, as rumors of an imminent eruption swept through Santorini's villages. Within hours, the island's only port at Athenios became a bottleneck, jammed with cars, buses, and clusters of people clutching suitcases and phones. Ferries scheduled for the tourist season now loaded at double capacity, their decks packed with families, workers, and tourists desperate to leave. No official order had been issued, but the steady drumbeat of earthquakes and the swirl of unverified messages on WhatsApp and Facebook convinced thousands to flee. The air was thick with confusion. Some heard there was a government alert. Others relied on word of mouth or panicked calls from relatives abroad. Hotel manager Andreas Papadakis watched as guests abandoned their rooms with barely a word, their faces pale, eyes fixed on the horizon. In less than a week, thousands had left the island, overwhelming ticket offices and leaving entire neighborhoods eerily silent. No one could say exactly how many had gone, but the exodus was unmistakable. The speed of departure outpaced any official response, leaving authorities scrambling to coordinate transport and reassure those who remained. For many, the fear was not just of the volcano, but of being left behind as the island emptied in a matter of days. Beneath the Aegean, the crisis reached its technical peak as scientists traced a dike, an underground sheet of magma, cutting a path 13 kilometers long from Santorini toward Colombo. Ground-based GNSS stations and satellite data revealed a pattern of deflation on the island. 6.8 million cubic meters of volume disappeared from Santorini's shallow reservoir as the dike advanced. The numbers left little doubt. Magma was moving laterally, not just upward, at a pace between 0.1 and 0.5 kilometers per day, fast for a system of this scale. Every day, the dike's tip fractured new rock, reactivating ancient faults and triggering swarms of earthquakes that kept residents and scientists on edge. Yet even with this torrent of data, thousands of quakes, centimeters of ground movement, gigabytes of waveform analysis, one question loomed over every calculation. Would the dike break through to the surface or stall in the depths? The models offered probabilities, not certainties. The dike's journey was mapped in real time, but its final destination remained hidden, a reminder of just how much about volcanic forecasting still lies beyond the reach of even the most advanced instruments. On January 24, 2025, at 2:19 a.m., Santorini's seismic network recorded the first of over 28,000 earthquakes that would follow in just 6 weeks. Scientists traced magma migration from depths of 13 kilometers toward the surface, confirming the existence of a shared magma system between Santorini and the Colombo submarine volcano. Ground deformation data revealed that nearly 300 million cubic meters of magma intruded beneath the island, while a 13-kilometer dike advanced northeast at up to half a kilometer per day. More than 11,000 people evacuated, highlighting the real-world impact of these underground processes. Yet critical questions remain, especially about the precise triggers of dike propagation and the full risk posed by submarine faults, which lack complete monitoring. Historical records show a repeating cycle of earthquakes, uplift, and eruption, but the exact timing of future events remains unknown. Today, GPS sensors continue to detect subtle ground shifts. The evidence confirms that Santorini's volcanic system is active and interconnected. The next eruption is not a question of if, but when.